Friends, our next topic is magnetic field due to a straight wire carrying current. Let us consider a straight wire conductor XY lying in the plane of paper, which is carrying a current I in the direction X to Y. Let P is a point, at a perpendicular distance A from the straight wire. Clearly, PC is equal to A. Let the conductor is made up of large number of small current elements. Consider one such small current element ideal vector of the straight conductor at point O. Let R vector is the position vector of point P with respect to this current element, and theta is the angle between current element ideal vector and R vector. Let CO is equal to L. According to Biot-Savart law, magnetic field dB at point P due to this current element ideal vector is dB is equal to mu naught upon 4 pi ideal sine theta upon r square. Now in right triangle POC, this is theta and this is phi. Theta plus phi is equal to 90 degree. Taking phi to right hand side, theta is equal to 90 minus phi. Therefore sine theta is equal to sine 90 minus phi. Therefore sine 90 minus phi is equal to cos phi. Therefore sine theta is equal to cos phi. Let us call it equation 2. Now cos phi is equal to cos phi क्या होता है भाई? Cos phi होता है base upon hypotenuse. Base is A, hypotenuse is R. Cos phi is equal to A upon R. Taking R to left hand side and cos phi to right hand side, R is equal to A upon cos phi. We call it equation 3. And tangent phi is equal to perpendicular upon base. Therefore perpendicular is L, base is A. Tangent phi is equal to L upon A. Therefore L is equal to A tangent phi. As L is equal to A tangent phi, differentiating this, left hand side become dl, as A is constant. Differentiation of tangent phi is secant square phi d phi. Let us call it equation 4. Now substituting 2, 3 and 4 in equation 1, we get dB is equal to mu naught upon 4 pi I. dl, in place of dl we write A secant square phi d phi. Ideal sine theta, in place of sine theta from equation 2, in place of sine theta we write cos phi, and upon r square होता है, in place of r we write A upon cos phi. Therefore this become A square upon cos square phi. A square upon cos square phi become A square into secant square phi. Cancelling common factors, this become mu naught I upon 4 pi A cos phi d phi. Now the direction of dB according to right hand rule is perpendicular to the plane of paper directed inwards, and all the current elements, similarly there are number of current elements, all the current elements, they are producing magnetic field in same direction. All the current elements are producing the magnetic field in same direction. Therefore total magnetic field at B due to current through whole conductor can be obtained by integrating equation 5 within the limit minus phi 1 to phi 2. Minus phi 1 is here, phi 1 is this is phi 1 and this is phi 2. This can be obtained by integrating equation 5 within the limit minus phi 1 to phi 2. As it is in downside, this is taken as minus, and it is in upper side, it is taken as plus. Therefore B is equal to dB integration from minus phi 1 to phi 2. Now dB is mu naught I upon 4 pi A cos phi d phi. Taking the constant factors outside, mu naught I upon 4 pi A, taking outside, it become cos phi d phi. Integration from minus phi 1 to phi 2. Integration of cos phi is sine phi. Limit of integration is minus phi 1 to phi 2. Substituting upper limit and lower limit, it becomes sine phi 2 minus sine minus phi 1. As sine minus phi 1 is equal to minus sine phi 1, therefore it becomes sine phi 2 plus sine phi 1, and we can also write it as sine phi 1 plus sine phi 2. Therefore this is the magnetic field at a point due to straight wire conductor carrying current. Now the special cases. When the conductor XY is of infinite length, is of infinite length and the point P lies near its center, then phi 1 and phi 2 both are equal to 90 degree. Therefore, B is equal to mu naught I upon 4 pi a. In place of phi 1 is 90 degree, in place of phi 2 is 90 degree. Sin 90 is 1, sin 90 is 1. This becomes mu naught 2 I upon 4 pi a. Or we can write it as this can write as mu naught I upon 2 pi a. When the conductor xy is of infinite length and the point P lies near its end y, conductor xy is of infinite length and point P lies near its end y, then phi 1 is 90 degree, phi 1 become 90 degree and phi 2 is 0. Therefore, B is equal to mu naught I upon 4 pi a, sin 90 plus 0. Sin 0 is 0, sin 90 is 1. Therefore, this becomes mu naught I upon 4 pi a. Therefore, magnetic field due to infinite conductor near its center is twice than magnetic field near its end. Magnetic field due to infinite conductor carrying current near its center is twice than near its one end. If the conductor is of finite length, say L, and point P lies on right bisector of conductor, then phi 1 is equal to phi 2 is equal to phi, sin phi is equal to perpendicular upon hypotenuse. This become L upon 2 upon a square plus L upon 2 का whole square. This become L square upon root 4a square plus L square. As B is equal to mu naught I upon 4 pi, sin in place of phi 1 is phi, in place of phi 2 is phi. This become this, substituting value of sin phi from this become this. And if the point P lies on the wire conductor, अगर point P straight wire conductor पे lie करता है तो phi 1 और phi 2 0 हो जाएंगे. Therefore, putting phi 1 is equal to 0, phi 2 is equal to 0, sin 0 is 0 होता है, तो therefore B is 0. Therefore, magnetic field at any point on the straight wire conductor carrying current is 0. Now, direction of magnetic field. Now, the magnetic field due to straight wire conductor carrying current, magnetic field due to straight wire carrying current, this is represented by magnetic field lines in the form of concentric circles with their center on the conductor, and the plane of these circles is perpendicular to straight wire conductor. If the direction of current is from A to B, then magnetic field lines they are anti-clockwise, and if the direction is from B to A, then direction of magnetic field line is clockwise. This can be remembered with the help of right hand rule. If we curl the fingers of our right hand and keeping the thumb perpendicular to it such that direction of thumb gives the direction of current from A to B, then the direction of curvature of fingers, this gives the direction of magnetic field lines. Similarly, here also this direction of magnetic field lines associated with the straight wire conductor can be determined with the help of right hand thumb rule.